Hello everyone. Today, this video lesson is going to be on floating point multiplication, and the way it's going to be formatted is we're going to start by reviewing scientific notation to give us the fundamentals on which floating point theory is based off of. And then we're going to do some floating point calculations. Then we're going to make a Verilog module to do floating point multiplication. So we're going to make the actual hardware that's in your calculators. So start to give you an idea of the steps that are taken to calculate it in hardware. It's best to show it with scientific notation. So let's say we wanted to multiply these two numbers. You would first rearrange it like this, and normally you would just, convert this to 7,400 and then to just 920 and then just add them. And then multiply them. Like normally you'd do that, but that's not the process that's taken by your computer. So we're going to emulate that using this. So the first step, hold on, is to rearrange. Make that neater. Rearrange it. 7.4 times 9.2 10 to the 3 times 10 to the 2. So once you have it like this, the first step is to multiply these two numbers. So then if you do that, you're going to get 69.56. And then second step is to add, because you know it's going to be times 10 to the 3 plus 2 equals 5. So let's just write that as 5. And then there's one last step. So the last step is to simply shift by 1 and increment the exponent if needed. And the reason why we do this is because in scientific notation, like proper scientific notation, the number has to have only one digit in front of the decimal. So just 7, any number that is less than 10. If you have something like 69.56, that's not in proper scientific notation, so it needs to be shifted. So we go to 6.956. So because we moved the decimal to the left, we need to increment the exponent by 1. So then this number here is the final answer. So that's how scientific notation works. Minutes. So now let's go over a floating point example. Floating point numbers, we're going to do double precision because that's what's used in better systems. So let's say we have a number A. Number A is going to be stored with 64 bits, where We're going to have a sign bit, 11 bits for the exponent value, and 52 bits for the m value. And the formula is going to be plus or minus 1 dot m 2 to the e is 10 23. So yeah, let's do an example. Suppose we have 0. We got 1, 3. So this is going to be, so these 11 bits here is the mathematical equivalent of 1026. That's our exponent value. And then let's say our mantissa or m value is going to be this. So so if an input a is equal to this, so we want to calculate what the number a is using that formula. So we want to convert this floating point number into something we can understand. We would just use this formula. So using that formula, it's going to be, oh yeah, let me write it down. Sin e m be equal to, so 1 dot m, just delete that, move that here, we would delete this, and move that there, and now the next step is to convert these numbers into things we can understand. Start off with this one. So, oh yeah, let me go through this slowly so people who don't understand can understand how to convert that number from binary to decimal. So the index, this is 0, 1, and it goes on, and then this is 10 because it's 11 bits wide. So we're going to do 2 to the 10 plus 2 to the 1. And the reason why it's 10 and 1 is because the places where there's 1, that's where the corresponding index are. So like, let's say this was a 1, that's 1, 2, 3, 4, 5, 6, 7. Then we'd have like plus 2 to the 7, but we don't have that. Okay, so let me get the calculator. 2 to the 10 plus 2 to the 1, 2 to the 10, 2 to the 1, 1026. So now that we know what that is, we can simply just erase this. Or you know what, I'll just keep it there for now. So we know that this is actually 1026. An unsigned binary. And then now we've got to convert this one. So it's going to be 1 plus 2 to the negative 1 plus 2 to the negative 2. And the reason why is because this is index 0, index negative 1, index negative 2, 2 to the 0 plus 2 to the negative 1 plus 2 to the negative 2 is equal to all this. Plus 2 to the 0 is just 0. So then that is going to be equal to, let's see what that's equal to. I think I can do it in my head, but just use the calculator just to be sure. Let's take on 1.75. So now that we know what those values are, we can just rewrite it all. So it's going to be 1.75. Hold on. Times 2 to 1026 minus 1023, which is 3, so we can just replace it as 3. So then that is, see what that's equal to. 0.75 is 2 to the 3. It's 14. 14.0. So that means is A is storing 14.0. So that's how you would store that. And let's say we have another, let's say we have another binary number. Oh yeah, let me do another one. Just one more. Because we need 2 numbers to do a multiplication example. Oh, hold on. In the sign, we know it's going to be plus because it's 0. This 0 here means we use a plus, so it's going to be plus 1.75. If this were, hold on, if this were a 1, then it would be negative 1.75. And the formula, like formally written, is like negative 1 to the s. If s is 0, the whole thing, negative 1 to the 0 is equal to 1. If it's negative 1 to the 1, then the whole thing becomes negative 1. So that's why having yeah, here, let me just move it up. Or so negative 1 to the s power times it all. So remember, if s is 0, negative 1 to the 0 is 1, so then the whole number is positive, which is our case. So we're going to do one more binary conversion, floating point conversion. So let's say we have 0, 1, 2, 3, 1, 2, 3, 4. So it's that. Okay, so we have this binary number, and we want to convert that binary number into decimal. So Using the formula, it's going to be plus 1 dot all this times 2 to the all that minus 10, 23. So then it's going to be, here, let me just use my calculator just to find out what it is. Let me write the steps. So 1, 2, 4. Times 2 to the 1. Oh yeah, let me show you something. If any of you have a CAS calculator, you can do some pretty good stuff. Zero B 1 0 0 1 1 0 0 1 0 1. Okay, so it's 1029. So that we know now that this number right here is 1029. Got that instantly from just typing that out. So we didn't need to do the whole 2 to the 10 plus 2 to the 1, 2, 3, 2 to the 3 plus 2 to the 0. Oh, wait a minute. This would be 0, 1, 2. Oh, so this would have been 2 to the 2. So that'd be 1029. But we didn't have to do that because this calculator can just do that instantly, which is super helpful. And it does only unsigned. So then it's going to be 1029 minus 23. So that means it's 2 to the 6. Or so hold on. What if it can just do the whole thing? Oh, I don't think it can do those. Oh yeah. Okay, well then never mind. So 1 plus 2 to the negative 2 plus 2 to the negative 4 times 2 to the 1029 less than 23, 84. So that means, so this was all equal to 84. That means that this is storing 84. All right. Now that we have two numbers, let's go about how we would multiply them using floating point. And we're going to do it using these two values. So let's do that real quick. So we got A, we got B, So yeah, all of this just shows you how to get the number that is stored in there. Just really wanted to make that point clear that this whole 64-bit value is actually 14. This whole 64-bit value is actually 84. So A is 14, B is 84. So that we're going to multiply both of those. But now we got to do it using, we need to apply these steps to this. And the way we're going to do that is converting it into a number. So if you can recall, A was represented by this. And this whole thing would be 3. And then, hold on, and then it was plus, so we can just have it be implied. Or, no, let's keep it. And then B was this. And that was 2 to the 6. So all right, and then we got A and B. A is equal to this, B is equal to this. So the first step is going to be to write it in the good format. So we're going to combine both of these. Oh, yeah. All right, so if we're going to multiply A times B, here, hold on. A times B. First step is going to be to take the fractional part, put them together, multiply them, take the exponent part, multiply them here, the 2 to the something. Kind of like how it's synonymous with the rearrangement step here. Now that that's done, step 1 is going to be to multiply this by this. So all that's going to be doing is using just normal binary multiplication. So let's do that. This is a 1. The first one's a 1. So we copy all of this once. Add 1 0 as a placeholder. This next one is a 0, so it's all zeros. Add 2 placeholders. This next one's a 1, so we copy the whole thing. Let me get the spacing good. Okay, copy the whole thing, so 0 0 1 1 1. So then the next one, what on earth? So the next one is 0. So then that means it's going to be, oh, no, there's 3 placeholders. And because it's 0, that, there's next row, last one, 4 placeholders, and then we copy it. Now we just need to add everything up. And remember, since there's 1, 2, 3, 4, 5 bits, the output needs to be 10 bits long. Because that's just a rule of binary multiplication. If you have 2 inputs multiplied together, the output is always twice the bit length. So if you have 4 bits times 4 bits, you always get 8 bits. Or if you have 5 bits, 5 bits, you always get 10 bits. That's just how the hardware works out for fixed point multiplication and things like ripple carry adders. So 0, 0, 1, 1. When you have 2 ones together, you do 0, carry. 2 ones together, 0, carry. When you have 3 ones, you do 1, 1. 2 ones, 0, 0. 2 ones, 0, 1, 1. And then let's count the bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's good. If there was no carry, like if this was just a 0 plus a 1 and there was a 1, we would need to know to write a 0 there to make the whole thing be 10 bits. That's important. And then something you just memorize is that the decimal point becomes here. It's always going to be here. It doesn't matter if there's more bits, like if you do 1 dot, I don't know, 1, 0, 0, 1, 1, 0 times 1 dot, all of this, when you do your steps of multiplication, let's say that, I don't know what the answer to this is going to be, but let's say you get a binary value of 1, 1, 0, 0, 1, 1, and then it's just a bunch of stuff. The decimal point is always going to be in the second spot. Always, always. When you multiply 2 things that are 1 dot. So just memorize that. Okay. So now that we've done step 1, we can do step 2. Which is 2. So step 2. Step 2 is going to be 2. 2 to the 3. Plus 2 to the 6 is equal to 2 to the 9. So that's all you do. So we multiply these 2 to get this, and we multiply these 2 to get this. Or not. Well, so step 1 was to multiply. Step 2 was to add the exponents. And when we do that, we get this. Now though, in this step, just how there was a step 3, where we had to move the decimal to make it be in the right format, and then increment the exponent, we had to do that here. We're going to need to move that back, so then the whole thing becomes let's do the 10. Because remember, when we move the decimal this way, this number becomes smaller. So to compensate for that, to keep it equal, we have to make this one bigger. Let me write some notes that'll be useful later on. So we need to think about, oh, something here, let me write something. Step 3. So there's really only two cases that are going to happen. Either the most significant bit is going to be a 1, in which case you're going to need to shift it in an increment, or the front would have been 0, 1 point something, in which case you don't really need to do anything, you're just done. So yeah, now that we know that this is our answer, we need to convert it to floating point, because that's what it's always going to be. So we know it's going to be 0, because remember, it was a times b. These were both positive, so it's going to be positive 0. Okay, make that in black. Zero. And then, so this is like our m. And then the value in here is always going to be 1023 greater than this. So 1023 plus 10 equals 1033. Then we need to convert that to unsigned binary, which our calculator will do just nicely. 1033 base 2. So then that means 1033 is equal to 1, 0, 0, 4, 1, 0, 1. So this number here is that. So then we know that that is our exponent. So that would be the product. And one really important thing is that if your most significant bit is a 1, then what that means is you just take all of the bits after, put them there, and then you increment. And then yeah. So then 10. If it wasn't 1, 0, if it was like 0, 1, like if it was 0, 1, hold on. So hypothetically it was 0, 1 dot, and then that same thing. And then you would take from here and put that there. So that would be like the most significant bit is equal to 0 case. And then you would not increment. So then that means 9 plus 10, 23. So that's just a different hypothetical. But anyway, this was our number. So let's convert that number to make sure that we multiplied a and b correctly. Just a and b 14 times 84. That's the answer. So that means this, oh, hold on. This should be that. Should be. So let's confirm. So it's going to be 1 dot our mantissa times 2 to the this. What is 10, 23? Let's find out what this is. Oh, wait a minute. We already did. It was 1033. Okay. Oh, so then it was just 10. Okay. But then that part, so it's going to be RB plus 2 to negative 3, 4, 5, 6, 7. 2 to the negative 6. Oh, hold on. Okay. So then that'll be 2 to the negative 6 plus 2 to the negative 7 times 2 to the 10. And that should be that. It better be. So let's see. 1 plus 2 to negative 3 plus 2 to the negative 6 plus 2 to the negative 7 times 2 to the 10 equals that. So what that does is that confirms that this number is equal to this, which means we successfully multiplied. So hold on. This would be like number C is equal to this. So that means A times B. Hold on. That pink. So remember, A was 14, B was 84. So both of them multiplied together give us that, which was this. Oh, it's too hard to add that at the top. But yeah, you guys get the point. So now that we've gone over how to do floating point multiplication, it's time to build the circuitry for it. So hold on. I'll pull up a different example real quick. So this is a very comprehensive example. Shows two possibilities. one where this floating point number is multiplied by this floating point number. This top one, the mantissa gets moved there. This minus 1023 means 5 is being stored. This mantissa goes there. 1027 minus 1023 means 4 is being stored. You do the step 1, multiply these two. You get this value. 5 plus 4, 2 to the 9. You look at this. Because the most significant bit is 1, you're going to copy this value into the mantissa of your final value. Then you're going to take the exponent field and then add 1 and then store that in here. And then in this second case, same thing. Everything goes on. But when you multiply, you get 0, 1. Because the most significant bit is 0, you copy these into your floating point value and you use this value directly. So now that you know that, now we can begin to make hardware for it. So step 1 was to multiply. Hold on. So step 1 was to multiply our 1.m's 1.ma times 1.mb. So the way you're going to do that is you're going to need an array multiplier. And remember, the mantissa bit is 52-bit. The mantissa field is 52 bits wide, which means a 1 dot all of this or a 1 dot all of this is going to be 53 bits. So that's like MA, that's MB. And we're going to need to multiply both of those together. So the way that's going to be expressed is 1 tick B1 and then MA. And then this will be 53 bit unsigned multiplier. So this circuitry here is going to essentially do this. You feed this value in, you feed a 1, and then your mantissa, and it'll output this. So we'll call that fractional product. So this right here was like the fractional product. Step 2 is to do this. So how would we do that? So for A and B, hold on. So we had 120 126 here and 129 there. Okay. So remember, this was actually, what was it? It was 3, right? Yeah. 2 to 3 and then 2 to 6. So remember, this exponent, even though it's 1026, using this formula at the top, it's going to be 1026 minus 1023. So it's actually 2 to the 3 that's encoded. Same thing here. Even though it's 1029, it's actually 2 to the 129 minus 1023, which is 2 to the 6. Which means that when we multiply A times B together, the end result we're going to want to get is 2 to the 9. Which means that the encoded value in C, so C equals, it's got its own sign bit, EC, MC, EC is going to be 9 plus 1023 because it's always encoded. The actual value in the number is going to be represented by a value that is 1023 bits higher. That is just how, and the reason why that is that that is just how floating point was made. It's not something for us to question, it's just part of the standard. So yeah, when we have, for step 2, it's going to be adding, step 2 is to essentially do what we did where we added 3 plus 6 to get 9. Yeah, right here, we added 3, added 6, got 9. As nice as it would be to just do that directly, we have to essentially 3 plus 6 equals 9. We get to do that using these two values. We need to take this value. We need to take this value. And then we need to determine from those two values 9, which was this. So 1032. Oh, wait a minute. Yeah, 1032, because that's 9 plus 1023. So we need to take EA and BEB and determine hold on, let me take a step back. Okay, let's continue. So the goal, hold on, let me move all this down into another step. That's probably why it's so confusing. Oh yeah, we gotta write it down. So 2 to the E, A, to the E, B minus 1023. So then 2 to the E, C minus 1023. Because remember, this is the encoding value for 3. This is the encoded value for 6. This is the encoded value for 9. And it would be nice if we were given just 3 and 6 and 9, but we're not. In our input value, we're given, oh yeah, let me write that down. We're given EA and EB. And using what we're given, which is EA and EB, we have to calculate the encoded value for that, which is this one right here. So, hold on. Just real quick. Okay. So there's a formula, fortunately, that will always be the same, where you take EA and EB to get the EC. And it's going to be EC is equal to EA plus EB minus 1023. So let's test it. EC equal to this plus this minus, let's just keep it simple. Should be equal to 9. Or actually, no, it won't be equal to 9. It'll be equal to this. Wait a minute, no, it'll be equal to EC. Yeah, what was that? Let me see. So 1026. It's 1029. It's 1023. It's equal to 1032. Yeah. 1032. And then that converted in binary will be this. So this right here is going to be what's stored to represent 9. And the way that's going to be done, so we're going to need a combinational block. Yes, the hardware that we're going to need to make is a combinational block that does this. Remember, EA and EB are both 11 bits wide, but we're going to make it be a 12-bit adder. And it'll have an 11-bit output. And the reason why that is to protect against overflow, we're going to add EA and EB like this, where we have a 0 at the end. Into B0. And this will be that, yeah. Yeah, so that would be our step 2. And then step 3, would be to make a third combinational device that let me go to a different example. Well, not example, but I have it all written out. It'll be faster that way. Yep, so there's all this. Hold on, let me find it. Okay. So this is the overall block diagram of the structure. So you're going to feed in your input A, which has got an S1, 11 bits for E1, 52 bits for M1. Then your second floating point value is going to have a bit for S2, 11 bits for E2, and 52 bits for M2. To do step 1, we're going to do 1 concatenated with this binary value multiplied by 1 concatenated with this binary value to get a 106-bit product. And then for our step 2, we're going to take our E1 and our E2, add them together like this, minus 1023. And then from this 12-bit value, we're going to take the first 11 bits and call them eTemp and put them out. So these two things right here achieves the effects of step 1 and 2. So like for this floating point value, step 1 would accomplish all of this through doing this. So you take 1 concatenated with this times 1 concatenated with this to get this, which is what you will get from multiplying it up. Step 2 is going to be to just use adders to compute this. So in step 2, you take 5 plus 4 to get 9. Well, we don't have 5, we have 1028. We don't have 4, we have 1027. And we don't actually want 9, we want 1032, because each of the actual value is actually stored with something 1023 bits higher, which is, yeah. So using this formula, we take E1 plus E2 minus 1023, you get 1032. So 1032 is what 9 should be. So after doing steps 1 and steps 2, we determine that this right here is the value. And then step 3 is going to be to assign MF and EF based off the most significant bit of step 1. And then also find sign. So okay. So in this case, because the most significant bit is 0, we use these as our final mantissa. So our MF is going to be those bits right here. And then EF does not change. It's going to be the same thing we calculated here. And that's that. Oh, no, let's do this. Except the product is changing into this format. So that means is we're going to shift the decimal this way, and then we're going to increment this. So what that means is we're going to take, so let's start with MF. So these values are going to be used as our MF right here. Because when you do the shifting, all of these become the thing that comes after the decimal. So that's why I use these. So MF will be the 52 bits starting after the most significant bit. So MF is all of that. And then, because we shifted it, we need to add one to the previously calculated exponent. So we add it, and we do that. So that's if the most significant bit is 1. And then using that, that's our value. And then we got our sign. So if we go back down to our block diagram, so these are relatively straightforward. You go down, and what you're going to need is you're going to need a multiplexer for the 2 possible scenarios. So you're going to take the most significant bit of your product from step 1, and then if this is high, the temp is going to get incremented by 1 and be used as your final. If it's high, you're going to use the first 52 bits starting immediately after the most significant bit if it's high. So that's going to be this case right here. Because remember, this is a 106-bit product. So this right here is index 105. You're going to copy index 104 all the way down to index 53. Oh, wait a minute. Oh, wait, no. Oh, no. So this is index 105, and that's index 104. Yeah, so then you're going to copy, yeah, you're going to copy index 104 to index 104 to index 53, which is all of this. And that is going to happen when it goes through here. So yeah, that's how that works. And then your sign is just the exclusive OR of S1 and S2. So this right here is the very simple version of everything. In reality, you're going to have that, and then you're going to have a multiplexer that will select the final product based on special scenarios. Let's say A or B, one of them is 0. Let's say A is 0 and B is, I don't know, like 57. Then rather than going through this whole process and calculating this, we're just going to set it to 0 no matter what. Or let's say we have positive infinity times negative infinity. Like A is positive infinity and B is negative infinity, or the other way around. Then we're going to just set it to be where this floating point, the floating point representation for negative infinity gets steered up no matter what. Or let's say we have something that's not a number, nan, getting multiplied by any one of these other things. If that happens, then like let's say A is the floating point representation for nan, and B is the floating point representation for anything else. It can be infinity, negative infinity, 0, something else. Then no matter what, it's gonna, this combinational network module IN3 it's going to select 2 for NAND, and then it's going to know to instantly set the final product to that. So this combinational circuitry right here handles all the special cases. This top level part just handles the actual calculation for normal numbers. Okay. Just to make it super clear, before we go into the Verilog demonstration, where I show the code for each of these blocks, we're gonna let's just go through it all one more time, just so everyone truly understands. Yeah, so I wanted to go through it live instead of just reviewing, just so people would be forced to think and be engaged. But yeah, let's go through it one more time. It's mainly just this last page, and then this. It's mainly just these 3 pages that we'll go over. So we're going to multiply 2 floating point numbers. Got 0 there, 11 bits storing 1028. That's our 52-bit mantissa. Assigned bit is 0. 1027 is stored in a binary value there. That's our mantissa. Then when we do our multiplication, it's going to be 1 dot this mantissa times 1 dot this mantissa times 2 to the this value minus 1023 and then this bottom one is going to be 2 times this value minus 1023, which is 4. So in reality, it's 5 and 4 being stored, but because remember, floating point always encodes it where the thing the actual value stored is going to be, which is 5, is going to be, or 4 is going to be 1023 lower than the value stored in your floating point input. So let's say we want it, well, when we want to have this number be inputted, we represent it like this, because 5, this will always be 1023 less than this. So to do step 1, we just take a 53-bit array adder unsigned to multiply these 2 values, and we get this. To do this, we can't just add 5 and 4 because we're not given 5 and 4. We're given 1028 and 1027. So we use this formula to get the encoded value that is, because it's the actual numbers 2 to the 5, and the actual number here is 2 to the 4. That means the actual number is going to be 2 to the 9. And because we want 2 to the 9, it means that the thing that needs to be stored is going to be 1023 greater than 9. It's going to be 1032. So in order to get 1032, we need to use this formula, E1 plus E2 minus 1023. And that's what we do. And then, so that's this. And then for step 3, there's going to be 2 cases. Either the most significant bit is a 1, in which case you use all the bits that come after. From here, 52 bits down, that'll be your final mantissa. And then you just use the exponent u. No, then you're going to need to increment your exponent by 1 because it's shifted. And then you use that here. So, yeah, this was the product. Because the most significant bit is 1, we're going to shift it so it shifts. Then we need to increment the 9 to 10, but in reality, it's going to be 1023 greater than what we're dealing with. So it's going to be 1023 stored. So then that goes there. And that's this case. In this other example, steps 1 and 2 happen exactly the same, except in our product, we get this. Because the most significant bit is a 0, in other words, it's in the format we want, we just use this value directly. Since this is 9, we can move what 9 is represented by 1032. So we just use that. Even though it's 9, in reality, it's going to be 9 plus 1023 in the floating point format. I mean, in reality, it's 9, but 9 is represented by a value that is 1023 greater, which is this. And then we just copy these values instead. So rather than copying these values, we copy starting 2 bits after the most significant bit, which is here. So we take these and put them there. And that's that. So these bits, these circuits, will execute steps 1 and 2. This last one, if it's case 1, if the most significant bit is a 1, normalization is we're gonna need to do the shifting. So we're gonna add 1 to the exponent, and then we're gonna select the bits immediately after it to be our MF. If it's a 0, then you don't do anything to the exponent, so it just passes. If it's a 0, then you choose bits 103 to 52. Yeah, to remember. That's bit 103. And that's bit 104. And then the most significant bit is 105. So that is the entire block diagram for that, and that gets fed into this. There you go. Now that you all understand the theory behind that, it's time to go into the circuit that implements it all. Man, a whole hour. Hold on. It's loading. All right. So this right here is the Verilog code for it all. Hold on. So this right here is this. This module is this. This module is this. The case indicator, that's IN3, that's this. That's 5 to 1. That's IN4. Oh yeah, and here it's IN2. IN2. And then same thing for the top one's IN1. Yeah. So now that you know that, let's go and look at it. So the multiplier, so this right here, this multiplier, the thing that would mathematically do all of this, it's right here, is literally implemented with just this simple module. You take two 53-bit inputs, have a product, assign the product to be A times B. Now, this is a very behavioral approach. You can manually make the circuitry yourself, which in previous videos we have done, but for our purposes, this is what's needed from a proof of concept. And this will synthesize, it will synthesize and work in a real circuit. Like if you want to get this on a board to calculate values in real time, or you're actually a manufacturing company making calculators, you could use that. The Verilog code will make an integrated circuit that will do exactly that. And then this module, so add A, subtract B, it incorporates this functionality here. So this step 2 is done by this, and the code for that is here. So in the instantiation, we have the most significant bits of our inputs be a 0. And then we put in the 11 bits for the two exponents. And it's going to be, remember, it's the formula EA plus EB minus 1023. So when you do that, you get this intermediate result. And then there needs to be 11 bits because there's only 11 bits for floating point. So that's why we assign that to this. So that's already this module and this module. Now let's go over this one. So the normalizer takes an A and B right here, S1 and S2. Remember, for the floating input for A, the very first bit's a sign bit. Floating input for B, very first one's a sign bit. So this is the sign bits of A and B. Let's go to the normalizer. So SF gets assigned to that. Assigned. And then we'll go over this part. So there's going to be two cases where E temp is coming in. If end product is if the most significant bit of end product is 1, we're going to want to add 1 and then pass it through. If it's a 0, then you just use it directly. So that is implemented here. Yeah. And then for the last one, for our mantissa, we do this. If it's a 1, you do this path where you take the bits coming immediately after. Like right here, oh, hold on. Like right here, you take bits 104 all the way down the next 52 ones. You do that if it's a 1. If it's a 0, you do the other case. Like here, let me bring that over. Like right here. Then you grab bits 103 to 52. So that's the normalizer. So those are the 3 inputs that handle the actual calculation. But then for the full functionality where you include the special cases, you're going to need a multiplexer, which is this simple circuit implements the mux. We take our 5 floating point inputs, 1, 2, 3, 4, 5, index 0 to 4. Got our select line, 2 bits of that, 3 bits of that to represent all the numbers. And then we select between them all. And then the thing that cell comes from, it's going to be module IN3, which is the case selector, case indicator module. And all it is just a huge combinational block going over all of the cases. So if A is NaN or B is NaN, then you're going to set the indicator to 2 no matter what. So this first case handles what happens if A or B is not a number. If A or B is not a number, then we're going to want to make the output be, we're going to want to make the output of IN3 be 2, so then this mux can then know to make the final product be an output of that. And then we have our 0 cases. If A is 0, or if B, oh yeah. So this is A is 0 with a positive sign. This is A is 0 with a negative sign. If either one of these things happens, then assuming it's not NaN, then the indicator, hold on. Oh yeah, so then this case will happen if B is NaN. If it's NaN, then indicator is 2, kind of like this case. If it's anything else, then it's going to be 0. Wait a minute. Yeah. This should be correct. If it's not correct, it's very, very easy to change. You just change the if statements. But I'm fairly confident that it's correct, and the reason, let's just show it to you. But yeah, the point is, it's just a combinational block that behaves how you want it to behave. So now let's run the simulation. So then I'm going to do this. So these are all, hold on. These are all of the test cases. And if you look, like if you do the math, they all work. 5.76 times this is that. This times this is that. 1 times 2 is 2. 3.14 times itself is 9 point something. 20 times 32 is 640. 0 times 2 is that. And we've got some cases with infinity. Infinity times a normal number that's not negative is that. Infinity times a negative number is negative infinity. Infinity times 0 does not exist. NaN. A number that does not exist times the number that does exist is a number that does not exist. Positive infinity times negative infinity is negative infinity. This times this is equal to that. Here, let's zoom in more. And yeah, so all the possible cases seem to be working. Well, they are working, at least when it's done like this. Maybe we would have to do it one more time with B having all the values in the top, which it should behave the same because this code, it's symmetrical, where there's like an else if, it checks both A and B. Like, yeah. So that is how you would build a floating point multiplier in hardware. So this entire block diagram describes the circuit needed to do floating point multiplication in the real world. And that is represented with all of this code. Each module is represented by a different block in this diagram. So yeah, if you got any questions, feel free to ask them in the comment sections. The next video will be on floating point addition. But yeah, I hope this helped. And that is all for now. All right. Later.